Welcome to our channel. Please subscribe for more updates. Cambridge International AS and A-Level Physics Coursebook by David Sang et al. Chapter 20, Oscillation. End of chapter questions. Let's answer number 1. State and justify whether the following oscillators show simple harmonic motion. A. A basketball being bounced repeatedly on the ground. Answer is no. There is a constant acceleration due to gravity. B. A guitar string vibrating. Answer is yes. There is a restoring force that is directed towards the center, and acceleration is directly proportional to displacement. Letter C. A conducting sphere vibrating between two parallel, oppositely charged metal plates. The answer is no. There is a constant force between the plate. Therefore, the charge will travel with constant acceleration towards its plate. D. The pendulum of a grandfather clock. The answer is yes. There is a restoring force towards the equilibrium position, and therefore the acceleration is directly proportional to displacement. Let's go to number 2. Number 2, the frequency is here, 1, and therefore your this period, and of course your F is equal to 1 also, 1 Hertz. Now omega is equals to 2 pi times F, or 2 pi over T. Write down an equation to describe the displacement x of the pendulum bob with time t. So let's go to letter A. The original equation is equal to x is equals to x sub o sine omega t. We replace the value. We have in terms of, it's good if you can express your answer in terms of centimeter or meter, does not matter. So I'll write her in terms of centimeter. So 4 sine, the value of this is 2 pi times 1 is 2 pi, so it's 2 pi times t. Let's go to B. BI. Okay, BI. The maximum velocity of the pendulum bob, the formula is, maximum velocity, formula is VO, maximum, omega times XO, amplitude maximum. Using this equation, you will get around 25.13 cm per second. PII, its velocity when the displacement is 2. So you're going to use the formula of the velocity at any point in time is equal to omega multiplied by the amplitude square minus the displacement at any point in time square. Using this formula, you will get around 21.75 centimeter per second. Let's go to number 3. Number 3. The mass is given 50 grams, is attached to a securely clamped spring. The mass is pulled downwards by 16. We have here the amplitude, or XO, alright? So that is your XO or amplitude, this part. Now, and released, which causes to oscillate with simple harmonic motion of time period. So you have your T, okay? Now, calculate the frequency. The frequency is 1 over T. So by doing calculation, it will give us 1.19 Hertz. Okay. Calculate the maximum velocity. Again, VO is equal to WX sub O. You can calculate your omega, 2 pi times F here. Now, the answer is around 119.5. So we can just round off to 120 meter per second. Okay. You are going to convert your mm to meter. 16 mm is 16 times 10 to the minus 3 meter. Let's go to C. Calculate the maximum. So letter C, maximum kinetic energy. So if you want to calculate the Ka maximum, it should be 1/2 mv squared. Okay, maximum also. So by this, you have your VO, you have your mass, you can calculate. That's around 3.6 times 10 to minus 4 joule or joule. That's the answer. Let's go to letter D. By the way, at which point of the oscillation will have this velocity? The answer is as it passes through the equilibrium position. So that is your answer. This passes through the equilibrium position. That's right. D. Write down the maximum gravitational potential energy of the mass relative to equilibrium position. You may assume that the damping is negligible. So we know that at two extreme points, when kinetic energy is maximum, the GPE is minimum, right? So it means to say that GPE max is equal to the KE max. So the GPE maximum is the same. It is 3.6 times 10 to minus 4 joule. Let's go to number 4. Okay, in number 4, in each of the examples in figure 20.37, give the phase difference in terms of fraction, degrees, and radian. Alright, let's start here. We are going to find the period. Period is here. This is your T. How many blocks is this? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8. So now we are going to answer this one. Okay, let me adjust. So here the first one is the fraction. What is the fraction? The fraction is this one, 1, 2, 3, 4. So it's 4 over 8, or this is 1/2 cycle. Okay. Now, in terms of degrees, 1/2, they are facing each other, it's 180 degrees. Half of 360 is 180. Okay. In terms of radian, this is pi. Okay, pi radian is 180 degrees. Let's go to the next picture. Okay, the next picture, again, we're going to determine our period. Our period is around at this point, so there will be 8 boxes going there. The difference is these 2 boxes. So 1 is the cycle, that's 2 over 8. Alright, this is just equal to 1/4 cycle. Okay, and we know that 1/4 cycle, so in terms of degree, we know that 360 divided by 4, this will give us around 90 degrees. Okay. And what about the radian? So you have 2 pi divided by 4 is pi over 2. Pi over 2 rad. Okay. Now let's go to C. Okay, C. Again, we need to find the period. The period is here. It's the same. It's 8 boxes. The difference is 1, 2, 3. So 3. So let's go to number 1. 3 over 8. Cycle. Okay, number 2, 3 times 360 divided by 8 is 135 degrees. And number 3, or triple I, it will become 3 over 8 times 2 pi. Okay, 3 over 8 times 2 pi. It will become 3/4 over pi radian. That's number 4. Let's go to number 5. Okay. So in number 5 here, determine the frequency and the period of the oscillation here. Okay. From this graph, the period, we see the period here is 8. Okay, 8 millisecond. So here the frequency we can calculate 1 over 8 times 10 to minus 3 because it's milli. This will give us around 125 hertz. Done. Now next is use and copy the graph on the same axis, velocity and the acceleration. So we are going to make the graph. Let's make the graph. Now, we know that, we know that the x is, the displacement is sine. We know that the velocity is the cosine, the first derivative, and the acceleration is the second derivative. So second derivative takes the sine function but minus. So it's better to start with the graph of the acceleration because it's sine function but in the opposite direction. So it's here. Opposite of this graph. Exactly opposite of this graph here. So this is your acceleration. It's here. My graph is wrong, so I need to erase that one. This part. Okay. There you go. Okay, that is your acceleration. So this is your acceleration here. Now let's move to the next one. Let me change the color. So to distinguish, the other one is the velocity. Velocity is cosine. So it's easy. It's the equilibrium position is here. It is where the maximum velocity is located. So it's here. So it is opposite to displacement. With displacement maximum, it's minimum. It's here. When the displacement is minimum, the velocity is maximum. So it's here. When the displacement is maximum, it's minimum. Okay. When it is minimum, the other one is maximum. Okay. It will go to minimum. Right. It will go to maximum. So it means to say that our graph looks like this for the velocity. Alright, So this is your velocity. Done with number 5. Let's go to number 6. Okay, for number 6, Cambridge syllabus only require sinusoidal. So here, state and explain if the body is moving with a simple harmonic motion. The answer is no, it is not moving at simple harmonic motion because the displacement here is giving us a constant gradient, positive and negative. So the value of the gradient is constant. And if I am going to comment on this particular graph, it's difficult to change your direction without slowing down. But for additional information, although this is not part of the Cambridge syllabus, we will answer this one for additional information, how to get this one, how to graph this one. So in order to get the graph of the displacement versus time, let's divide the graph first. So that we can explain the graph. The purpose of this cutting is for us to graph. Okay, this one. So the gradient of displacement is the velocity. The gradient velocity is the acceleration. Let's start. Here the gradient is positive, so we can put it here at the top. That's the gradient. In this case, this part here, the gradient is negative, so you can put it here. It's constant, by the way. So here it's positive, the gradient is positive, so you can put it here. Now the gradient of this is here. The gradient is a small positive here. So you can connect the graph now. This one, this is now your graph. Just connect your graph. This is your velocity, the gradient of displacement. Let's go to velocity. The gradient of the acceleration, the gradient of the velocity is the acceleration. So here, at this point, let me change the color. All right. At this point, no acceleration. But when you change your direction, positive velocity to the negative velocity, then you have an acceleration here. Okay. Then again, this time you are in negative velocity here, and then you're changing to positive velocity, then you have acceleration here. And then from positive velocity, you're changing to negative velocity, you will have another acceleration here. That is all. Please don't forget to subscribe for more updates. Thank you.